So that's the end of this lesson, and it's the end of our entire discussion about Hough transform. It's an interesting example of a general approach. In this case, it's voting that was first developed many years ago, like I said, back in the 80s, which resurfaces in sort of more sophisticated forms as things come along. In fact, there's something recently called Hough forests. And Hough forests combine the Hough offset ideas that features vote for offsets with an ensemble or a collection of classifiers similar to random forests, and that's why these things are called Hough forests. Fortunately for you, you're only going to be using the basic Hough transform for lines and circles for your problem set. It's more work than it looks, so make sure you leave plenty of time. And I think after you get that working, you'll have an appreciation for what it means to get these more sophisticated methods to work. All right, welcome back to computer vision. So let's see. So we did the images as functions for a little bit and started talking about edges, and then we took a little bit of a detour where we talked about Hough transform in terms of extracting information using those images as evidence. So now it's time to get back just a little bit to image processing. And this lesson and one more or maybe two more beyond this, we're going to be talking about what's called frequency analysis. Now in the old days, that is, and that's actually pretty old already. Now we're talking 40 years ago, 30, 40 years ago, all of you who would be working on images, you would actually have been electrical engineers. And you would have spent a lot of your time studying this stuff that we're going to be talking about extensively. You define your filters and other types of image analysis operation in terms of what's called frequency response. That is how things change when you have high frequency stuff and low frequency stuff. But most of you are much more oriented to computer science, where we tend to think of images as data structures and not so much as a signal. But some of this understanding is still critical. This is especially true for a phenomenon referred to as aliasing. I know many of you are familiar with aliasing in a sort of image perspective where you see the little jaggies because you've got a line that doesn't go perfectly straight. But it's actually a frequency phenomena. And in fact, the goal of this lesson and the next few is to get to a point where you could talk about aliasing from a frequency perspective. And it'll teach you why, for example, if you have an image and you want to make it half the size, you shouldn't just throw out every other row and every other column. That's the wrong thing to do. And by the time we're done with this, you'll see sort of why that's the case. Here's a picture, a very famous picture, and the question is, what do you see? All right, so most people probably first see the kind of stylistic drawing of a naked woman, and then maybe if you look, you'll see down here, there's a picture of Abraham Lincoln. But if you take a look at the title of the picture, this is a painting by Salvador Dali, and it's Gala contemplating the Mediterranean Sea, which at 30 meters becomes a portrait of Abraham Lincoln. Now, you don't actually have to step back 30 meters. We can just blur the picture. And when I blur the picture, it looks like that. And aha, there's Abraham Lincoln. And so the question is, what's going on there? All right? And loosely, the answer is that at this image, there's all this high-frequency information that's showing you all these squares, and you see the outline of the woman, and you can see what she's looking at, something in the distance, and you can see that picture of Abraham Lincoln. But at the low frequency, it actually is a reasonable picture of Abraham Lincoln. And the idea is that images can be, actually any signal can be decomposed into a set of things that describe it. And we're going to get to frequency, but really what we're talking about is what's referred to as a basis set. So what is a basis set? So here we've lifted this from Wikipedia, edited a little bit. So a basis set, B, well, you have to talk about a vector space. So something is a basis set of a vector space, V, is a linearly independent subset of V that spans V. So let's expand those words out just a little bit. So let's suppose we have B that's just these vectors V1 through Vn, and it's just some finite subset over this field. So a field comes from mathematics, but let's just talk about the real or complex numbers. Okay, then a basis set B if it satisfies the following conditions. So linear independence, okay, basically means that if I have some different constants, A1 through AN, so these are constants. If I take a constant times each of the vectors, and I've got a different constant, and if the sum of those is 0, then it has to be the case that all of those constants were 0. This is no different if you think of this in two dimensions. If I have two vectors that are not in the same direction, then if I combine them, right? I get this answer like that. Well, the only way that distance can be 0 is if both of the coefficients are 0. So that's linear independence. And then there's what's referred to as the spanning property, okay? That, remember, it spans this vector field. And what that means is that for any vector in that vector space, I can create it by just some linear sum of the basis set. And again, you know, basically the idea is, so we normally think of a basis set as being perpendicular, but it doesn't have to be, right? So if I've got this and I've got that as my two basis elements, and I want to create a vector that's like that, then basically what I have to do is I have to take some multiple of the horizontal plus some multiple of the vertical will get me to that picture. By the way, most of you are used to basis sets being orthogonal, okay? So, you know, x and y. All we said they had to be was independent, okay? Now, it's helpful if basis sets are orthogonal. We'll talk more about it in a minute. Because what it means by orthogonal is, in order for me to figure out how much of the x there is in a vector, I don't have to worry at all about the y, because the y amount doesn't affect the x amount because they are orthogonal. Another way of saying that is if I take a vector and I take a dot product with the x direction, I get one value, and a dot product in the y direction, I get another value. Well, if I take each of those dot products times their basis vector and sum them up, I get back the new vector. And that's just because x and y are orthogonal. And that's why it's helpful if your basis sets are orthogonal. But technically they don't have to be, they just have to be independent. That'll let you reach any vector. If we had a basis set for images, and we'll talk a minute about what that means, that could be probably useful for analysis, especially for linear systems, because we could consider each basis component independently. Why is that true? Because remember, in linear systems, things just sum. So if I could say how some operator applies to each element of the basis set, and then I just have to scale it and sum it, then I know how this operator applies to the entire image. And that's part of the reason that we're going to go through this whole basis set decomposition, is because most of our operations are going to be, that we'll be considering, are going to be linear operations. And when I was talking about things from a long time ago in filter theory, etc., those are all based on a linear types of operations. To consider basis sets of images, what we're going to do is we're going to think for now of an image as just being a single point in a very large space. So if I have a space that's an n by n image, right? So let's suppose it's 100 by 100. So 100 by 100, that's 10,000, okay? So you can think of the entire image as just a 10,000 dimensional vector. If you wanted, that would be fine. Okay, so what would be a basis set for a 10,000 dimensional vector space? Well, one particular basis set is just our usual one, right? We do zeros, except we have a 1 in one of the elements. That's like x and y and z and p and q and r, and you run out of letters before you get to 10,000. But basically, you have a 1 in every place. Now, are these independent? Yep. Because if I sum up a whole bunch of them, the only way I can get to a 0 vector is if I have a 0 multiple of each of them. Because they're independent, they don't affect one another. But it's really not a very helpful basis set, because each one of these basis vectors, that one, that's just a single pixel. So telling me about sort of how it behaves with respect to a single pixel, that's not a particularly helpful basis set. Instead, we're going to look at a different kind of basis set. And it's a basis set that considers this image, or any image, in terms of how quickly it varies in different directions. So here you see an image that is just, no variance stalls. You can think of that as just a constant intensity. And as you move to the right, it starts to wiggle faster and faster and faster. As you move down, it wiggles faster and faster and faster, but this time horizontally. And then if you combine them, you would get these different orientations. And by the way, the two different pictures of the blue and the green are sort of, you can think of these as kind of like sines and cosines, kind of offset. Now, this particular basis set has a name, okay? And it's referred to as the Fourier basis, or Fourier decomposition. And it's named after this dude, Jean-Baptiste Joseph Fourier, okay? So he had a crazy idea in 1807, that any periodic function, that's a function that repeats, could be rewritten as a weighted sum, try to say that quickly, rewritten as a weighted sum of sines and cosines of different frequencies. In other words, you can make any repeated pattern, doesn't matter what it looks like, as long as it eventually repeats, using sines and cosines. So don't believe it? Well, you wouldn't be alone. Back at the time, there were some other folks you may have heard of, like Laplace or Poisson and other mathematician types. They didn't believe it either. A lot of controversy. There's a question about whether Fourier's proof was correct. Turns out his result was correct. And in fact, it was so controversial, it wasn't even translated into English until 40-some-odd years after his death. But like we said, it is true. And the series now that he's dead and famous, we call this the Fourier series. All right? We're going to get from Fourier series to Fourier transform to discrete Fourier transform, just so you know where we're headed. The idea is that if you have a signal, the signal has as its building blocks these sinusoids. And if you add enough of them, you can get whatever component you want. So here we're adding up different, this was our target. These are the elements that we're adding. We're going to show this more in a minute. And this is the function that we're building up. So before we look at that more carefully, how many degrees of freedom are there in this signal? Right here, okay? There are 3 degrees of freedom. What are they? Well, A here is just going to be amplitude. That's going to be a scale, all right? And then there are these 2 numbers, omega and phi. And omega is what's referred to as the frequency, and phi is the phase. So which of these is most important? Which of these encodes the notion of a coarse signal versus a fine signal? Well, it's going to be this one, the frequency, right? So as you change that frequency, as that number gets bigger, essentially the thing wiggles more quickly. To give you a little bit of a notion of sort of frequency and time, et cetera, and pretty soon we're going to throw time away because we're only going to be interested in space, but since you talk about how quickly something wiggles, and it originally was derived from one dimension, we'll talk about it this way. So here I have a signal, okay, g of t, okay, that's made up of 2 parts, okay? It's got a sinusoid of some frequency f, and then another sinusoid of 3f, but it's been scaled to make a third. So that's this signal here, and you can write that as just the sum of these 2 sinusoids. After all, that's what this equation says. And because of linearity, the stuff just sums, the combination of the 2 on the right gives you on the left. And if I were to draw out sort of the contributions of the sinusoids to the signal, it would look like this. Okay, so this is written in this particular way. I'm only showing you positive frequency. We'll talk about negative in just a minute. But whatever f is, the idea is that the signal here has a frequency spectrum with a certain amount of power at f and sort of 1/3 of that at 3f. Okay, and this is one form of drawing out the spectrum. We'll talk more about spectra in just a minute. You'll notice that this picture on the left is sort of kind of approximating getting towards a square wave. And it turns out that actually, if you really wanted a square wave, what you do is you keep adding these odd frequencies, all right? And I want to show you this because sometimes people will ask, well, how can I get sort of a sharp boundary using just smooth sinusoids? So here we have our original picture, and now I take that original one and I add in something that wiggles at 5 times f, and you see that I'm getting closer yet to a square wave. And then I get to 7 times f, and what comes after 7? 9. And what you can see is that we're getting closer and closer to having this as a perfect square wave. Okay? And in fact, you can show that a square wave can just be written as this infinite sum, okay, of these frequencies. Okay? And the amount of power you need goes down as the frequency increases. All right? So what we want to do is we want to get to a point where we can look at a signal and say, process it in a certain way or compute with it in a certain way to say, what are the sinusoidal components that go into making up this image? And in fact, you can show that to do a square wave like this, you need an infinite sum of decreasing amount of increasing frequency, and that's what's shown here. Now, what I haven't done is I haven't talked to you at all about phase. And in fact, I'm not talking at all about, you know, what the phase, right? I could have this offset or I could have different elements offset. And in fact, all I'm showing you here is the amount, or you can think of it as the power, we'll talk more about that in a minute, of the content of each sinusoid. And the reason we're not talking about phase is our goal is not to reconstruct an image. We just want to, typically what we're going to want to know is how much power there is in each of the different frequencies. In computer vision, we're interested in sort of analyzing what's going on. If we're actually going to reconstruct images, then we would probably have to worry more about the phase to get you better reconstruction. But we're not going to do that today. Given this idea that any signal, certainly any periodic signal, can be made up of a sum of sinusoids,